we'd like to do today is we'll go through this example here. So what you are asked to do is to design a column where you're softening. So you're asked to design a ion exchange column to soften about 0.88 cubic meters per second of water, given the temperature of 10 degrees C, and you're told that the raw water has a total hardness of 400 milligrams per liter as calcium carbonate. Similar to MSUs, you're told that you want to soften it to a concentration of about 100 milligrams per liter as calcium carbonate. You're given some design parameters. For instance, we'll use a column diameter of 3 meters. You're told to use a Dubalite C20 resin. We will use sodium chloride to regenerate the resin, which means that we're going to use the resin in the sodium state. And you're given a number of design parameters. Now, one of the things that is important to note is this term leakage. Here is our column. It is in the sodium form. This is our water to treat. If the column is perfectly regenerated, the concentration initially would be 0, and then it will start to increase. And we've got some breakthrough concentration when we would regenerate. But nothing is perfect. What we have is what we refer to as leakage, where the concentration of the effluent is 1% of the initial concentration. So even right after regeneration, we have about 4 milligrams per liter of hardness in our effluent. It's not 0. Now, you're asked to soften to 100 milligrams per liter. How am I going to achieve that? This, under these conditions, will be 4 milligrams per liter. This is 400 milligrams per liter, but what I want to achieve is a water with 100 milligrams per liter. So what can I do? How can I solve this problem? This is what I want. I'm starting with 400. The effluent is 4. What can I do? What if I do this? So what if I bypass a fraction of the flow? So this is 4 milligrams per liter. This is 400 milligrams per liter as calcium. All of these are as calcium carbonate. And what I want is 100. So what I really have is a mass balance problem. So that's what I'm going to use. Okay, I'm going to bypass some portion of the flow around the column so that I don't have to treat the entire flow, but yet I end up with a water that has about 100 milligrams per liter. What's the advantage of doing this? Or what's the disadvantage of having a water with essentially 0 hardness? Corrosion, dissolution of your pipes, red water. Exactly. The water is extremely corrosive. Okay. So by adjusting this bypass, we can produce a water that has a positive LSI, okay, that is slightly scaling, protects the pipe, and is not corrosive. Also, very softened water tends to almost feel kind of slimy. But the major thing is corrosion. So you're given a number of parameters. We'll use these parameters in the design. And we'll use the graph in just a bit. Okay. So let's start by converting to equivalents per liter, because why? You're given your capacity in equivalents per liter. So we have 400 milligrams per liter as calcium carbonate. We divide that by the equivalent weight, 50 milligrams per milliequivalent, and that is equal to 8 milliequivalents per liter. The effluent that we want, this is our desired effluent, has a hardness of 2 milliequivalents per liter. So back to when we talked about equivalents per liter. The concentration in the effluent due to leakage is 8 milliequivalents per liter times 0.01 or 0.08 milliequivalents per liter. So the next thing we need to do is calculate this bypass fraction. So we have our flow in here to the column. And our flow out. So, and we're bypassing some portion. And what we need to find out is that bypass portion. So Q treat, we don't know. C treat is that leakage, 0.08 milliequivalents per liter. C bypass, we don't know. Sorry, Q bypass, we don't know. C bypass is equal to 8 milliequivalents per liter. And then Q desired is that value that we were given to begin with. And that is 0.876 meters cubed per second. And the desired concentration is 2 milliequivalents per liter. So we can write a mass balance. We need to make some assumptions. We're looking at the mass balance right here. What assumptions do we want to make? Okay, we've made, so we've got a final concentration there. Okay. What else? What other, we're writing a mass balance. So what other assumptions? Okay, so we'll use a fraction. Okay. So we're going to let the F equal the fraction bypassed. And we're going to assume that that's constant with time. So 1 minus F equals the fraction treated. How about this? When I put the little mixer, what assumption am I making? How about a CSGR? And we'll make the assumption that we're operating at steady state. So if you remember, the change in mass with respect to time is equal to 0. So we're making that assumption around the system boundary that I made. The column is not operating at steady state. What's operating at steady state is just this control volume right there. So with those assumptions, I can write that Q treat times C treat plus Q bypass times C bypass is equal to Q desired times C desired. So that's my basic mass balance equation. I can substitute using these relationships here, where so the treat is 1 minus F times Q total times C treat plus F Q total times C bypass is equal to Q total times C desired. So what have I done? I've substituted in so that the only unknown that I have is F. Okay, I know the total. And if I substitute treat, remember, so we've got 1 minus F, and notice Q total cancels. So Q total cancels, and I have concentration treated is 0.08 milliequivalents per liter plus F times the bypass 8 milliequivalents per liter equals 2 milliequivalents per liter. And F is equal to 0.242. So roughly 24% is the fraction I'm bypassing, and I'm treating the rest. So by bypass flow is 0.242 times 0.876 meters cubed per second, and that is equal to 0.212 meters cubed per second. And the treated flow is 1 minus 0.242, again, times the same flow rate, and that is equal to 0.664 meters cubed per second. Just want to check something. The next thing I need to calculate is the total hardness to be removed each day. So I start with 8 milliequivalents per liter. My leakage is that 1%, so that's not being removed, times the 0.664 meters cubed per second, times 1,000 liters per meter cubed. So meters cubed cancel, liters cancel, and multiply by 86,400 seconds per day. Seconds cancel, and that is 4.54 times 10 to the 8 milliequivalents per day. The total resin capacity is 1.45. Notice this is equivalents per liter, and that's liter of resin. Okay, where did that come from? We go way back up here. You're told that when you regenerate with 160 kilogram per cubic meter concentration of salt, the capacity is between 1.35 equivalents per liter and 1.56 equivalents per liter. I used roughly the average value. Okay, so it's just the average of the range given. So this is what we would call the theoretical resin capacity. So it's given by the manufacturer. However, life doesn't operate typically in theoretical ways. And there are competing counterions. There is short circuiting through the column that results in a resin capacity that is less than the theoretical, and that we refer to as the operating resin capacity. So we're going to reduce the theoretical, this total resin capacity, by 20%. So what we will use is 1.16 equivalent per liter as our resin capacity. We need to pick a depth. The depth should be, and what you're told is should be at least 0.5 and actually less than 0.95 meters. So that's what you're told by the manufacturer. And typically when you're designing these ion exchange systems, you're really designing it based on the manufacturer's specifications. You're also told that the service flow rate is in the range 16 to 40 bed volumes per hour. Okay. What is a bed volume? The volume of the empty bed. So this is 16 to 40 meters cubed of water per hour per meter cubed of bed. That's what we mean by a bed volume per hour. Okay. Could also be in cubic feet. Could be in gallons, gallons per gallon. That is what we mean by a bed volume. We'll use 24 bed volumes per hour, or 24 meters cubed of water per hour per meter cubed of resin. We said that we had a diameter of 3 meters, so that was stated. So the cross-sectional area, pi d squared over 4, is just pi 3 squared over 4, or 7.07 meters squared. Okay, and that was given. The volume of the column is just the area times the depth. And so this is 7.07 meters squared. We said we were using a column that was 0.9 meters deep, and that is 6.36 meters cubed. So this is our volume per column. Okay. To find the total volume required, this is the total flow divided by the loading rate. At 24 bed volumes per hour. So this is 0.664 meters cubed per second times 60 seconds per minute times 60 minutes per hour. So seconds cancel, minutes cancel. We're going to divide this by 24 meters cubed. Remember, this is water divided by hour per meter cubed of resin. So the meters cubed of water cancel, hours cancel, and we have the total volume of resin required. The number of columns needed, we've got 99.6 meters cubed total. We'll divide that by 6.36 meters cubed per column, and that is equal to 15.7 columns. So how many columns will we use? Exactly, 16. Good. Okay. The exchange capacity of each column is the operating capacity times the volume of resin. So we 1.16 equivalent per liter of resin times 6.36 meters cubed times 1,000 liters per meter cubed. Liters cancel, meters cubed cancel, and that is 7,380 equivalents, or 7.38 times 10 to the 6 milliequivalent, just to keep everything in the same units. The next thing we're calculating is the service time of the column operation. So we said we've got, here's our column, we've got flow in, we've got a bypass. When we're talking about the service time, what do we mean? What is the service time? Okay, it's the time, exactly. It's the time that the flow is going through the system where we're actually obtaining treated water. And this is the column capacity times the number of columns divided by the total hardness to be removed per day. So we have 7.38 times 10 to the 6 milliequivalents. Remember, that was per column. We have 16 columns. The total hardness to be removed, we calculated before as 4.54 times 10 to the 8 milliequivalents per day. So this is 0.26 days or 6.24 hours. So that means every 6.25 hours, what do? We're running bypass all the time. Okay? So the bypass is what we're running. But what's happening here? Over time, our concentration is increasing. So when we reach breakthrough, what do we need to do? Or when we reach this after 6.25 hours, roughly, what do we need to do? At that point, we need to regenerate the column. Okay. Because the concentration leaving this column exceeds the limit, acceptable limit. We're regenerating with sodium chloride, so salt. Next time you're in the grocery store or in Home Depot, someplace like that, you'll find, if you look for them, there are bags of salt, and they're actually sold as softening salt versus the salt that you put on the sidewalk in the wintertime to de-ice the sidewalk. Higher quality salt. So the total weight required per column, this 160 kilograms per meter cubed was given. We have 6.36 meters cubed, the volume of resin per column, and we need 1,018 kilograms of salt. Okay. So what you're told here, this is kilograms per resin. That's how much salt we need per volume of resin, and we're multiplying this by the volume of the resin. We'll assume a 10% salt solution, typical. So we need about 1,000 kilograms, but we want the weight of the solution, it's 10%. So it's roughly roughly 10,200 kilograms of solution. So this is kilograms of salt. It's 10% salt. So this gives us the salt solution mass. Okay. The volume of the salt solution that we need for regeneration is that 10,000, roughly 200 kilograms, divided by the density and the specific gravity of a 10% salt solution is about 1.07. Times the density of water, and that equals 9.51 meters cubed. This is the volume of the solution. Now we're going to use the treated water to make up this solution. So notice some of the water that we're actually producing, we're reusing directly to regenerate the system. The regenerate time we'll pick from the table. So we've got this table right here. Needs to be 1.6 to 8 bed volumes per hour. Notice it says 10 to 20% salt and tells us that we need at least 30-minute regeneration time. So we need to pick a flow. And let's start with 4 bed volumes per hour, and that is equivalent to 4 meters cubed of water per hour per meter cubed of resin. We have 9.1 meters cubed. Where did we get that? Back up here. That's our volume of our salt. We'll divide that by 4 meters cubed of water per hour per meter cubed of resin. This is our salt solution times the volume of the resin, and that is 0.37 hours. So the question is the standard operational flow completely stopped during regeneration? The answer is yes. In a home unit, this is typically done at night, and there's a storage tank. Okay, so it's done typically when you're not using water. In this type of system, you would have to have redundancy because if you have 16 columns and you're regenerating every 6 hours, you pretty much have a column under regeneration process at any time. So you've got to have redundancy at that point, okay, or provide storage capacity. So we said it had to be at least 0.5. So this is too low. So what do? Reduce the flow rate. Okay. If we reduce the flow rate to 3 bed volumes per hour, that gives us a regeneration time to be equal to 0.5 hours. The backwashing flow rate, actually, got this in. Sorry. The backwashing flow rate here, we need this graph. Now we want 50 to 75% backwashing. Okay. What are we doing during backwashing? We've gone through, okay, kind of thinking the sequence. We've got the service time. So we're at that point in time during service, we're removing the hardness. Following that, the next thing that happens is we regenerate. So at this point, we start with the resin in a sodium form. We're reacting the resin sites with the hardness. So we'll write it as calcium. And we now have our resin in the calcium form, and we're released 2 moles of sodium for every mole of calcium that we remove. Need to maintain equivalent. So what happens during regeneration? If you had to write a reaction, what would the reaction look like? Goes back, exactly. So here we're going to start with the resin in the calcium form. We have this concentrated solution of sodium chloride, and now we're restoring the resin in the calcium form, and we end up with a solution with a high concentration of calcium. Biggest challenge is what to do with this. What not to do with this, typically if you have a home use system, is do not put this in the septic system. Otherwise, you're shock loading the septic system and potentially killing the organisms that you need in the infiltration field. So after we regenerate, we're now going to backwash. During backwashing, what did we do in infiltration when we backwashed? And I'm going to end right with this question. But what did we do in the filtration system when we backwashed? We run backwash water to the waistline. So we fluidize the bed, right? We're trying to remove particulates. We do the exact same thing in an ion exchange system. So we're now running upflow, and we're looking at removing any particulates that were captured in the system. So continuing on, we said that with backwashing, we need an expansion of roughly 50 to 75%. So as mentioned with backwashing, what we're looking at doing is expanding the bed, fluidizing the bed to release any particulates that have been captured in the ion exchange column. So let's start with looking at 50% expansion. If we look at 50% expansion, we have a temperature of 10 degrees, and that would correspond to a backwash flow rate of about 10 meters per hour. So this would be backwash flow rate, 10 meters per hour. Now, typically, we want between 12 to 20 meters per hour as our backwash flow rate. So at 50% expansion, the backwash flow rate is too low. So let's look at 60%. If we go here, 60%, 10 degrees C, we'll do the same. And we're at about 12 meters per hour. So if we have 60% expansion, we have a backwash flow rate that is equal to about 12 meters per hour, and recognize that's meters cubed of water per meter squared of resin bed per hour. So that's what we're looking at. We also need a time. So let's go back to that table right here. And we need between 5 to 15 minute backwash time. So let's just pick the middle value. So we'll pick 10 minutes. So just need it to be between 5 to 15 minutes. Lastly, we need to rinse the resin bed. This is to ensure that we don't have residual salts, any residual particulates in the bed. And again, let's look back at the table. And for the rinse, we're looking at a rate of 80 to 40 bed volumes per hour and a time between 10 and 40 minutes. So let's pick value in the middle of that range. So we'll pick 24 bed volumes per hour, and we'll use 25 minutes. So we're just picking roughly in the middle. So now let's look at the total time for operation. We have service. So this is when we're treating, removing hardness, producing a softened water. And we said that that was 6.24 hours. We have regeneration, and that is 0.5 hours. We have backwashing, and that was 10 minutes. And we have rinsing, and that was 25 minutes. So we have 7.3 hours. So notice, this is when we're producing softened water. Rest of this time, roughly another hour, we're regenerating, we're backwashing and rinsing, and we're not producing water during that period of time. We would be relying on storage for that period when we're not producing water or redundancy, so we need additional columns. Now, the other thing we can calculate is the amount of water that we're actually producing versus the amount that we're using for regeneration, backwashing, and rinsing. So we said for regeneration, we needed 9.5 meters cubed. That was meters cubed of solution, but we need to use the water to make up that solution. For backwashing, we have 12 meters per hour. We'll multiply that by the surface area, 10 minutes, and 60 minutes per hour. So hours cancel, minutes cancel, and we have meters cubed. That is 14 meters cubed. For rinsing, we're using 24 bed volumes, so that's 24 meters cubed of water per hour per meter cubed of resin. And now we need to use the volume of the resin times 25 minutes times 60 minutes per hour. Again, minutes cancel, hours cancel, meters cubed cancel, and that is 63 meters cubed. So in total, we use 9.51 meters cubed for regeneration, 14 meters cubed for backwashing, 63 meters cubed for rinsing. Think about how much we're actually producing. We have 0.664 meters cubed per second. That's our flow rate. Total flow rate, we have 16 columns. So 1/16 of that is the flow through each of the columns. Operating for 6.24 hours. And there are 3,600 seconds per hour. Hours cancel, seconds cancel, and we're left with cubic meters. And this is equal to 0.0936. So roughly 9.4% of the water that we're producing is going back to be used for regeneration, backwashing, and rinsing. So we need to think about that when we're actually ultimately sizing our ion exchange resins so that we're assured of producing sufficient water for our needs. So hopefully this helps you understand the process by which we design ion exchange resins.